On behalf of the Institute of Indian Foundrymen Chennai chapter and MPM Infosoft Private Limited, it gives me immense pleasure to welcome you all to today's technical seminar on least cost robust charge mix optimization for cast iron foundry. In today's competitive foundry environment, cost optimization and process robustness are no longer choices, they are necessities. As Peter Drucker rightly said, efficiency is doing things right, effectiveness is doing the right things. This session is designed to help us to do both. We are privileged to have with us today Mr. Deepak Chowdhary, a well-known person actually in the foundry industry, founder and owner of MPM Infosoft, who brings decades of industry experience, and Mr. V. Rahul, software development professional at MPM Infosoft, who will share practical and data-driven insights on charge mix optimization using modern tools. With this, I once again welcome you all and hope this session delivers valuable insights that you can take back and implement into your foundries. I request our chapter chairman, Mr. Sendil, to do the welcome address, please.
Good afternoon, fellow Foundrymen. It gives me immense pleasure to welcome you all for this technical webinar, which is jointly organized by Indian Institute of Chennai chapter, in the Foundrymen Chennai chapter, and MPM Infosoft Private Limited. And we are privileged to have Mr. Deepak Chowdhary, sir, one of the richest knowledge person and foundry veteran in the market. And I think everybody is able to correlate Sandman with his name. And we are happy to be here. Thank you, sir. Thanks for your valuable presence. In fact, I just want to give a small background why we call for this webinar. In fact, Chennai chapter has recently conducted our 40th Ruby Jubilee celebration in Chennai, where MPM has presented this paper. Mr. Rahul has presented a paper, and the content was so attractive. I thought that this should reach us the bigger audience. And it was confined to only the people who could come in person to that particular seminar. And that is the purpose we requested again MPM Infosoft to present this paper so that it can reach out the most of the foundrymen across the India. And as you all aware that no foundry is shifting from arts to science. The earlier days, all things goes from the experienced people. It's all in their mind based on their experience. These charge mix are prepared. Now the slowly shifting to it's a science. I think people have moved to Excel sheet based on their knowledge. The Excel sheets have been created with people started widely using Excel sheets and in the foundry. I think few people have already launched this solution. I'm sure that the MPM with their potential knowledge in the market and foundry sector, this particular solution would give a lot of takeaway to Indian foundry industries. Like others, I'm also very keen to understand how this is going to help Indian foundry industries. And everyone is aware that this is a starting point. Charge mix is the starting point for your cost optimization or quality. Everything, it starts from here. It's a base level. And once this is right, I think everything goes right. And I'm sure it will have a lot of takeaways. And I once again welcome you all for this good webinar. I request my secretary to take forward. Thank you.
Thank you, Mr. Sendil. I request our council member, Mr. K. Hemprasad, actually to introduce the speakers actually of the day to the audience.
Thank you, sir. It's my honor to introduce today's speaker, Mr. Deepak Chowdhary, sir. He is the founder owner of MPM Private Limited, Nagpur, India's pioneering manufacturer and technical application experts of lustrous carbon additives for use in greens and molding. He started his career as a manufacturer of engineered pre-blended lustrous carbon additives in the year 1978. Being the first generation entrepreneur, he has devoted his entire 40+ years of his career in understanding the complexities of greens and molding process and its control in ferrous foundries. His passion for disseminating knowledge to foundrymen is evidenced by several IIF platforms where he has addressed on the subject, as well as presented India's first and only paper on the subject of green sand management, role and application of carbonaceous additives and concept of total carbon in a green sand system in the World Foundry Congress held in Chennai in the year 2008, and also presented a paper titled Data Analytics, the Next Dimension in Molding Sand Control at the 73rd World Foundry Congress held in 2018 in Krakow, Poland. He has also presented various papers at the Indian Foundry Congress and he has received the Best Paper Awards by the Institute of Indian Foundrymen for his paper titled Reducing Rejections and Optimizing Additive Consumption by Data Analytics, Machine Learning, and IoT, the next dimension for Industry 4.0 in foundries and molding process technology at the Indian Foundry Congress held in 2019 at Greater Noida. Mr. Chowdhary sir has once again turned entrepreneur to develop the world's first data analytical software, Sandman, for optimization of green sand with a view to reducing repetitive casting defects. He has also presented various papers at the Metal Casting Congress organized by the American Foundry Society, and one of his paper, Data-Driven Dynamic Optimization of Foundry Sand Testing, was received the Best Paper Award by the American Foundry Society in the year 2019. Following the success of Sandman, Mr. Chowdhary was instrumental in designing concepts for development of another algorithm, VComp-SP, Variable Compatibility Set Point, for which the Best Paper Award was presented to him by the American Foundry Society in the year 2021. Mr. Chowdhary sir has also authored a book titled Green Sand Solutions for Iron Foundries, a practitioner's handbook. Mr. Chowdhary sir is a BCom Honors graduate from Srindam College of Commerce and Economics, Mumbai University. He is also an alumni of 2015 batch owner President Management Executive Education Program by Harvard Business School. He was chapter chairman of Nagpur IAF and the chief spokesperson for the MIDC Industries Association Nagpur. He has been an invitee on several management institutes and likes to interact with students of entrepreneurship. It's my honor to introduce our next speaker, Mr. V. Rahul. He is a chemical engineering specialized in minor in systems engineering, AI, and ML from IIT Madras. Currently, he is working as a data scientist at MPM Infosoft Private Limited, specializing in data-driven solutions, predictive modeling, and optimization for industrial applications. He is also one of the authors of the journal publication in the field of foundry and metal casting, focused on cost optimization and data analytics for charge mix design. Now the floor is yours, sir. Thank you.
Right. Good afternoon, everybody. Fellow Foundrymen, I would say, not everybody. And this is a fraternity, one of the few societies in the world which is called a fraternity, that is a brotherhood, rather than just ladies and gentlemen. So I resonate with all of you on a very personal level. As I was telling Mr. Senthil Kumar during the first interactions we had while we were waiting for all of you, my career was actually launched from Chennai when I made my first bulk supply of raw material to Ennore Foundries in those days, which was located in Ennore. And I had the privilege of interacting with stalwarts like Mr. Ponuswamy and K. Ramakrishnan and all these greats of our industry who actually laid the seeds of the size of the industry that we are witnessing today. And so I have a very special corner and a very soft corner for this chapter. And I was telling him that I will be ever available to all of you, along with my team, for any program that you decide to organize on any subject which I can speak on. So thank you for that lovely welcome. Thank you, Mr. Senthil, Mr. Rajmohan, Mr. Hem Prasad, and all the office bearers of the IIF chapter for this kind introduction of my profile. It has been a long journey of almost 47 years. And it's a journey that I am proud of, because being a non-technical person, to be able to interact with highly skilled scientists and professionals like many of you who are seated here is indeed a privilege, and has always given me the ability to challenge myself to try to reach your levels of excellence. Coming to the topic, without much of further ado, I would like to just go a little into the brief into what is the context and how did this journey start and where is it going to take us as a foundry society, right? It's not just a topic that we are discussing today on least cost robust optimization. It is a small part of the role that artificial intelligence is going to play in our lives as we go forward. This journey was seen by me as far back as 2011 when I was doing a case paper in Harvard, and I realized that this is exactly what this industry needs to be able to do this multivariate, multi-causal analysis and analytics, which is virtually impossible for us to do on a human level and a human interface in the dynamic world of the foundry production and the dynamic environment in which the industry operates. We are one of the few industries in the world which start from non-standard scrap, and we are expected, all of you are expected to produce exacting specification, exacting dimension, finished products for your customers, which go into safety parts, aerospace, and what have you. This is really a great, example of how metallurgical engineering, thermophysical engineering, and all the associated, fluid dynamics engineering comes into play to convert scrap alloys into a final product with such exactitude. So far, this has been the realm of experience, as Rajmohan, I think, mentioned, and that's so very true. But as we are going ahead and foundries are touching significant production heights, speed, and complexities of the patterns and their increasing demand for dimensional and quality integrity of the castings from overseas buyers specifically, and which will soon be translated even from our Indian customers who actually consume these castings. We have to be at the forefront of being able to understand that it is no longer only in the realm of the human interface that this is going to be translated into reality. We are, in my opinion, already a little far behind, but the good news is that the rest of the world is not anywhere close to us either. We are very much in the forefront on technology, and I go around the world. I've been to the US, I've been to Brazil, many other foundry centers of the world, and I can tell you with complete conviction that we have some of the best technological brains and capabilities and machineries and facilities to be able to produce castings and claim our position as not only being number 2 or number 3 in terms of the production volumes of castings, but the quality and the technology of making castings for the world requirements. Now, the concept about this artificial intelligence, as everyone is so fond of, this is getting to be more of a buzzword. But there is a very fine line of distinction between artificial intelligence and machine learning, which I term as virtual artificial intelligence, because machine learning also learns from data and then translates that into an output. Artificial intelligence is actually the mimicking of a human brain and proactively taking action without the benefit of forward thought and with little benefit of hindsight, except the data that has been crunched and given to it, and the simulations that are being done in black boxes all over the world to give results which are not necessarily verified for them at that particular point of time. To give you a classic case in point, when we did the sand mix algorithm, we can give the recipe of a sand mix and give the results coming from that recipe even before the results are tested for the green sand properties. That is artificial intelligence. Whereas what we do in terms of predictive analytics is the realm of virtual intelligence. Be that as it may, we are going to be relying increasingly on sensors, IoT devices, in order to capture real-time streaming data and to be able to give optimized and real-time and accurate outputs in terms of casting outcomes, for example. This topic that we are going to discuss today is just a small subset of the entire grand scheme of the artificial intelligence universe that is right now before us. and which we have to find ways to embrace in some way or the other, and as fast as we can. Now, the situation here is that, as Mr. Rajmohan or Mr. Senthil said very correctly, that we relied on experience to do a charge mix calculation. But we always try to, for example, touch the midpoint of the limits of the elements that we are targeting. What you will see and what my young colleague, young and dynamic colleague Rahul is going to explain to you is how we use the entire space between the minimum and maximum points of each element to give a prediction or a prescription of the charge mix, which will help us achieve the proper and the correct charge mix and at the lowest cost first time right, hopefully. And I'm sure you will find it as interesting as you found it the other day when they were presenting in Chennai before you. And Rahul is a young man and he is cutting his teeth now and making his presentations. It is his, I think, the second presentation. So you will find him impressive, I'm sure. And I will now give it to Rahul to take this entire proceeding forward. Rahul, I will always be standing by your side. If you have any questions or you need to reach out, please feel free to reach out to me. Thank you very much.
Thanks a lot, sir. Good afternoon, everyone. I'm Rahul, data scientist at MPM Infosoft. Today, in this presentation, I'll show how least costly robust charge mix optimization for cast iron is designed using charge mix optimization and how charge mix optimization and metal digitalization can work together to improve cost, quality, and process stability. So, with that said, let me start. So, about us, we are a technology driven software company specialized in product development and digital transformation service. We operate as a sister concern of MPM groups, and we are strategically located at IIT Madras, fostering innovation through close collaboration with academia and industry. Our esteemed products are Sandman, PCSP, DigiSmart, with some of the upcoming seeming products like optics, metal analytics, and energy analytics. So first we'll go through the least costly charge mix, how it's being designed. Let me introduce what is charge mix. Charge mix is a combination of several scraps, metals, alloys, all brought together in certain percentages, melted together to form a cast iron or any grade, any products. The raw material composition significantly influences the chemical, mechanical, and the thermal properties. Optimizing the charge mix ensures consistent quality, performance, and the least cost in the final castings. Challenges that is faced by traditional methods is that we heavily rely on empirical rules and trial and error methods, and we are quite conservative in designing charge mix. By the way, conservative, I mean that we are trying to always target the midpoint of the target chemistry than operating within the target range that we are given with. So why do we need charge mix optimization? First is that we try to ensure the consistent quality in ferrous casting. This will help us to get final products at good quality. Second is cost reduction, where we try to maintain the quality. At the same time, we try to get the least possible charge. Third is resource utilization. We try to maximize the resources that are available with us, whether it is runners or risers, scraps, and try to minimize the amount of alloys that we are using. Next, we try to improve the productivity by getting the charge mix first time right, by maintaining its chemistry within the target limits, as well as we are getting the correct grade, tensile and hardness. Customization. Our charge mix can work for grades that the Foundry hasn't even seen before. Like we can design charge mixes that are up to FG 350, 360, 370 that Foundry hasn't done before. All it needs is just need to tell the charge mix that you need this grade, this tensile, this hardness, and this chemistry. The charge mix will give you the set of scraps to be added. Market volatility. So let's take the case. Currently, you're following a specific amount of charge need to be added to produce a grade. all of a sudden, one of the scrap price got increased. That means now the cost of production for the same scrap, so for the same grade, would increase. But with this charge mix optimization, we can mitigate its effects, thereby reducing the operational cost. So the objective of this charge mix optimization is as follows: to design the least costly robust charge mix for different grades of ferrous casting. So methodology. First, everything starts with data collection. We collect the 6 types of data: target composition, scrap composition, cost of the scraps, allowed range of scraps, which is a domain constraint, where Foundry mentions the minimum and maximum amount of scrap that has to be added. Like let's take 5% of bigger and should be definitely added for this for this heat. Those can be added to, as a constraint. Inventory data, what availability of scrap and alloys present in the inventory. This data is also fed to Chowdhary. And the scrap recovery. So the recovery of each scrap, each element of the scrap can also be fed into the charge mix. Based on that, the charge is being designed. All these data are done a sanity check where we make sure that the maximum composition in the target chemistry, the max composition is always greater than the min, and the fractions are always not greater than 1. And the problem detection. Here, our main goal is to reduce the charge mix, but at the same time, we get the required grade fall within the target specification, and the amount of scrap that is being added will be well within the furnace limits. Once this optimization is done, this model will try to give us the combination that gives you the least possible cost. At the same time, we meet the grades, that is tensile and hardness. So a typical charge mix formulation will be looking like this. Our objective is to reduce the total charge. At the same time, we fall within the chemistry and the furnace capacity. First, we went one step further. We thought, okay, we'll improve it by saying we'll still reduce the cost of the charge. At the same time, we maintain the target chemistry, fall within the furnace capacity. We try to utilize whatever inventory we have. Let's say if you don't have a certain scrap, still this charge mix will be working good and fine. Also, we thought we'll add an empirical relations for tensile and hardness based on the chemistry, like carbon, silicon, phosphorus, how they affect the final tensile and hardness. Those were also included into the constraints. And min and max scrap constraint, let's take Foundry wants to add 5% pig iron, a classic example. Those can also be added, and the low carbon scrap constraint. So we found one drawback in this refined formulation, the typical formulation. What was that? This formulation was an LP. So this gives us the best possible solution, the least costly charge mix that can be produced under this constraint. But what if our scraps has an uncertainty? Let's take a pig iron of carbon percentage as 4.18. Its carbon percentage is not always 4.18. If I take each scrap, each a pig iron scrap and see it, all won't be having the same 4.18 carbon percentage. Some might be having 4.1, some might be having 4.2, some might be having 4.5, maybe. So these creates uncertainty in the charge mix. So if I'm assuming that I'm going to produce a certain grade, and I think my carbon percentage in pig iron is just 4.2, but it turns out the actual chemistry was 4.5, then this data will be totally mislead us and makes our chemistry to fall out of the specification limits. So as you can see in the diagram on the right, this is the minimum and maximum carbon percentage that is allowed. And as our formulation is LP, our solution will always fall at the boundaries of the feasible region. So when we design an LP problem, and when there is uncertainty, there is a very high chance that our solution might fall out of the target specification. All these are caused due to the uncertainty in the scrap composition. So what we decided is we'll solve this problem by handling this uncertainty with robust charge mix formulation. We design the uncertainty as a P matrix. It's a big technical term. Basically, this P matrix is just to mention the uncertainty. And we are saying that now this new chemistry, J plus PU, will be my final chemistry. So the robust charge mix translate into this. Still the target chemistry, furnace capacity constraint, inventory constraint, tensile strength, hardness, scrap constraint, and low carbon constraint all are met while handling uncertainty in the target chemistry as well as during the mechanical properties like tensile and hardness. So the comparison between the typical and the robust formulation is as follows. Typical formulation works good as long as there is no uncertainty in the material composition. Once uncertainty happens, there is a very high chance that we will fall out of the target chemistry. But robust charge mix will handle these cases. But the thing is that this formulation will give a cost which is a little bit expensive compared to the typical formulation. Still, we'll be able to get our chemistry well within the target specification. So to test this out, we have done a case study on an Indian foundry, which produces almost 50,000 metric ton of automobile parts per year. This foundry produces grades anywhere from FG200 to FG300. And for our test case, we took a block component of grade FG241, which sees a tensile strength of 241 megapascal and a hardness of 221 hard newtons. So the required composition of the castings are as follows. The casting needed a carbon percentage of 3.25 to 3.25, silicon of 1.9 to 2.21, manganese of 0.65 to 0.75, chromium of 0.25 to 0.35, phosphorus of 0.04 to 0.08, sulfur of 0.06 to 0.08, and tin of 0.065 to 0.085. And the scrap composition is taken away, assuming this is the scrap composition, which we have taken it away. We have also taken that the furnace capacity to be 6 metric ton, and the foundry doesn't want to use any more than 10% of CI borings in the furnace, and a pig iron at least of 5% in the furnace. So the results were as follows. The foundry practice gave a cost of 56.05 rupees per kg, whereas a typical formulation gave the cost price of the charge as 55.636 rupees per kg. And the robust formulation gave a cost of 55.735 rupees per kg. So as you can see, it doesn't look like all these look very close. But when you take those to an yearly scale, assuming 5 heats per shift and 3 shifts per day, and a furnace capacity of 6,000 kg, the cost goes up to 9,810 rupees per kg, and a monthly increase of 2,13,000 and a yearly increase of 25,666. So this is how much rupees it will increase from a typical formulation to a robust formulation. But still, the robust formulation will give you an yearly savings of 81,64,800 compared to the foundry practices, which is almost up to $95K. Also, we can see over here when uncertainty happens, the typical formulation will fail you 99.2% of the times, which means you won't get correct the first 99.2% of the times. But during robust formulation, it's guaranteed that for 83% of the times, you'll get your target chemistry first time right. The cost savings are derived as follows. This is the comparison between the optimizer and the Foundry method. Here we can see the scraps are arranged in the descending order of its price. So the least costly one is at the end, and the highest costly one is on the left. So you can see the optimizer, which is the green bar, is trying to use scraps that are much cheaper compared to the Foundry method. Still maintaining the target chemistry, grade, and hardness. So the summary of this section is as follows. The robust charge mix optimization helps in successfully balancing between cost and constraint violation through the strictest factor beta. So with increase in beta, basically the strictest factor, which has to be increased during uncertainties, will give you a higher cost, but still you'll be getting your chemistry first time right. On the other hand, when there is no uncertainty, you can very well rely on the typical formulation, which will give you the least possible charge mix. So the proposed robust optimization framework empowers foundries with a data-driven, adaptable approach to charge mix formulation, ensuring cost effectiveness, quality control, and long-term operational sustainability. Yeah, so that's about charge mix formulation. But question might arise: how can we implement charge mix optimization? That's done with the help of digitalization. Robust charge mix optimization works on the assumptions and uncertainty. And the very assumptions are that we have all the data that was used while we were explaining the first section, like the cost, the six data that I told, the target chemistry, the cost of the scrap, the recovery, the inventory. Assuming we have all these data on a real time, that's how the charge mix works. By metal digitalization, we can convert all these assumptions into real-time facts. Without digitalization, Foundry has to be a little bit conservative in their safety margins, have to do higher alloy additions because we don't get the chemistry first time right. So need to add alloys to make it up. Limited cost savings. But with metal and melt digitalization, we'll be enabling the real-time spectro and the melt temperatures. You'll also get an actual idea of what is the recovery of each scrap and the burn off trackings, heat-wise learning, as well as box-wise learning, followed by model feedbacks. This way, we can be less conservative and more robust to our optimization, reduced alloy usage and scrap cost, which will reduce our operational cost, and higher first-time write heats, which improves the productivity. So the melted digitalizations are as follows. The following processes can be digitalized: inventory management, furnace digitalization, thermophysical data, spectro digitalization, inoculation and quality control, microscope and microstructure digitalization. So what is metal digitalization? Metal digitalization is the conversion of all the metal and melting parameters into real-time digital data using sensors, automation, and connected systems. This helps us traceability, visibility, and data-driven decision-making for grades, quality controls, chemistry controls, and cost savings. With the help of AI-based optimization, I can see someone has raised their hand.
We can respond to that as we go along, Rahul. You can continue with your listing.
Oh, okay, so with the AI-based optimization, our goals will be to reduce the cost, improve quality, increase throughput, reduce variability, and boost sustainability. Think of digitalization as not only turning the data into digital screens where we can see all the data no more. It will also help us to give our analytical skills, analysis skills, and make data to speak for itself. Why foundries need digitalization? The traditional challenges are manual record keeping, availability gap in real-time inventory, variability due to scrap quality and composition, which is the very purpose of the charge mix optimization, suboptimal charge mixes, higher rejections, and reworks. Basically, we don't know why the rejection has happened. Whether it's due to inoculation, whether it's due to chemistry or something. Digital benefits are as follows. It brings us real-time decision making, predictive quality control, cost optimization, transparency across operations, and root cause analysis. Okay. So the digitalization of the inventory, the first vertical. So earlier data had manual entries and monthly stock checks. That's the way it was done. And now after introduction of AI, we can do this with computer vision and IoT. With our very own cameras, we can identify which scrap is being loaded, and with the help of PLCs, we can also get the quantity of how much it is getting loaded. Also with IoTs in the bin, weighing scales in the bin, you'll be having a real-time tracking on how much of each scrap that you have in your inventory. So you don't have to keep on checking for the next charge, what should be added, what should be added. On. With digitalization, everything will be on the fingertips. So the key metrics are on-hand inventory, how much of each scrap we have, material movement rates, how much the material consumption rates basically, utilization forecast, how much material we are going to use based on the production schedule, if we have it, and the reorder alerts. This will help us to identify the bottlenecks in our upcoming schedule, and based on that, we can have a procurement management also. So the data sources are weighing scales, cameras, and computer vision, along with ERP systems. Furnace digitalization. Earlier, the manual temperature records, operator's judgment, which is very subjective, and limited historical data, because all data is notebook written, and we only measure it, let's take 15 minutes once, 1 hour once. Now, with real-time furnace monitoring with sensors, we get almost every second, every minute, every hour data in our hand with PLCs and digital dashboards. The key metrics are here are melt temperature profile, which is very crucial as it decides the viscosity and a very wide range of defects. Energy consumption, melting time per heat, furnace utilization, and downtime. So the data sources over here are thermocouples, pyrometers, power meters to understand how much energy consumption is being used, PLC or SCADA systems, and
Rahul,
furnace event logs.
Rahul, sorry to interrupt you. Can you elaborate on the melt temperature profile as we discussed yesterday? The advantages of melt temperature profile. Yeah.
Yes, so the melt temperature profile, uh, the idea melt temperature profile will give you an exact space and time of how much, what is the temperature of the metal of the melt that we are handling with space and time. So this gives an idea. Let's take if the temperature of the melt is less, which means the viscosity of the metal will be less. This creates misruns, cold shuns, and incomplete fillings. On the other hand, higher temperature will cause us oxidation, gas pickup, and metal penetration. Also, the temperatures are highly dependent on the casting profile. So thinner profiles will have higher cooling rates, and thicker profiles will be having lower cooling rates, which will directly affect the inoculation. A stable and well-controlled temperature profile ensures solidification, reducing thermal gradients that cause shrinkage, warpage, and internal stresses. This this directly improves the dimensional accuracy, repeatability, and consistency of castings across heats. Specific heat of scrap and the thermal efficiency. So here we try to just sorry about that. So why specific heat matters? The idea is that each scrap will be having a certain amount of energy needed to increase the unit mass of it by 1 degree centigrade. So each scrap will be needing a certain amount of energy in joules or calories to increase its temperature by 1 degree centigrade. And scrap percentage, X, Y, Z percentage into the charge will be needing a different amount of energy need to be used in the furnace to melt the scrap. So idea here is as follows. We create a scrap grade specific library made out of the historical data. Furnace heat sensors like thermocouples and energy meters will help us to create this library, along with energy models that will give us an idea based on how much this charge is being loaded, how much energy we'll need to melt this charge. This will give us precise energy plannings, less overfiring, and better melt turnaround. Spectrometer digitalization. So digitalizing the spectrometer will give us real-time chemistry and chemical analysis, heat-wise chemistry history, and trend monitoring of carbon, silicon, phosphorus, manganese, chromium, tin, whichever the crucial elements are down there. We can monitor them in a real time. This collection is done via LAN, USB, gateway directly into the DB, connecting the spectrometer directly to the DB. Outcome is auto comparison with the target chemistry. Basically, we compare what's the current chemistry and what is our target chemistry, whether we are lying within the limits. Based on that, we can decide our alloy addition whether we need to increase the chemistry or we need to reduce it. This is we can make a faster decision making out of it. Second is learning from the past hits using AI for reduced human errors, fewer retests and reworks and delays, and tracking the trace elements in the scrap, which is a crucial one, as the some trace elements can make the castings very hard, which can't be salvaged at all. Inoculation and quality control. Inoculation is the control addition of alloying or conditioning agents to the molten metal, typically just before pouring, to refine the solidification structure. It promotes the formation of fine, uniform grain structure by increasing the number of nucleation sites during solidification. In cast iron, inoculation helps prevent effects such as chill, carbides, undercooled graphite, while improving mechanical properties like tensile, ductility, and measurability. Proper inoculation also reduces section sensitivity, which I mentioned earlier, like the temperature profile has to be quite good for and the proper inoculation. This way, we don't fall into defects like carbides in the thin section and the formation of basically we try to make a similar graphite structure throughout the casting. Uh, Proper inoculation also reduces section sensitivity, stabilizes microstructure across varying wall thickness, and improve consistency from heat to heat, as well as box to box. Digitalization enables automated dosing based on recipe, real-time feedback via temperature or chemical sensors, AI-based recommendation, which will be done very soon, and box-to-box traceability of dosing. Data collected as follows: the metal composition and the dosing event logs, which gives us what inoculant is added and how much. Microscope and microstructure digitalization. Microstructure inspection is manual and very subjective from lab to lab, from person to person. Digital scope, connecting them to DB via LAN or gateway, gives us a real-time tracking of what is the microstructure that is currently being there, its graphite type, nodular count, and the flake distribution can be manually judged using machine learning computer visions, and the root cause analysis will be done very instantly. Based on the historical data, we might also get for this flake structure, what was the defects, or what was the uh, tensile state, what was the mechanical properties that was done, and using ML models like computer vision models, we can directly judge it before even the casting is being made. And the objective of this division is as follows: to quality assess the heat, root cause analysis, and feedback to the charge and metal practices. So we aspire to have a foundry that is fully digitalized, starting from the sand to metal, and finally till the shakeout. And within the metal, we try to capture the spectro, furnace, inoculation, microscope, wherever the data is possible, and try to bring everything into a meaningful data. The NPM Infosoft team wishes to thank IIF Chennai for providing us this invaluable opportunity to present our paper at the IIF Chennai chapter. Thanks a lot. So I think as we have time, I think we would like to show you all that. The charge mix optimization software that we have built, named as OptiCharge, that is present in Sandman. So this software takes in the furnace capacity, the heel, the previous component, basically what was the heel that was left out, its chemistry, which can be defined over here, heel chemistry, and the current learning block and its target chemistry, which all will be previously feeded into the system. Along with it, the scrap and alloy composition, even these will be feeded into the system. this scrap and alloy composition is based on the procurement date and the lot of the day of that date and the scrap and alloy range. This is where the foundryman can play by saying they need a minimum of 5% figure and only a maximum of 10% CI boring. They can't go, they don't have any of the CI borings or any of the tin coated scrap. Those things can be mentioned in the scrap and alloy range section. And the low carbon scrap range, basically the how much minimum and maximum percentage of the low carbon scrap that they want to afford it to get the tensile. Those can also be feeded into here. Once all these values are feeded in, we can also give the uncertainty in each of the scrap. Let's take our carbon percentage in MS scrap is totally certain. Then we give a value of 0. And based on the uncertainty degree, these values will start to increase. These data will be manually calculated by the software. So all you have to do is just enter the digital data and the software will take care of all these parts along with the recovery. Once all these data are fed into the system, on clicking design your charge mix, it gives you the component, the grade that we want, the tensile that we will get, and the hardness, the cost of this charge per kg, and how much of each scrap that you have to add to get this grade, this to fall within this target chemistry. So this can work for even different grades like FG241, FG260 grade with whatever grade the Foundry works. As I told, this software is formulation is totally customizable, tailored for Foundry needs. So yeah, thanks for this opportunity. Thank you, everyone.
Thank you, Rahul. As most of you are Foundrymen, you would have also guessed that besides your normal FG grades or SGRN grades, this is particularly very useful for alloy, for high alloy grades or alloy RN grades, where very expensive additives are used or alloys are used. This can be extremely useful. So yeah, thanks, Rahul. Rahul, can you take them back to that slide where we showed the melt and preparation infographic? I would just like to add some points of consideration for Foundrymen here. Now, it is not just about digitalization that we are talking about. Digitalization is a pretty simple act or an action or a design that can be done and executed. What is important is what comes out of this digitalization. What is the actionable output that we can get from this dynamic input, real-time input? So, for example, I just want to open the mind to consider that in the absence today that you have data coming from the spectrometer, you know the data of your CE meter, you know the data of your pouring, you should probably know the data per second dosage of the inoculants and the type of inoculant, the size of inoculants, and the quantity of inoculants. All these things can be optimized to be able to give you the first time right and optimal addition of each of these additives in your casting. Because we all know that too much or too little, both are bad. So we normally optimize these practices by manual trial and error, but when it is done through machine learning or artificial intelligence designs, they become extremely accurate. And you could then, correlate inoculation to the charge mix itself. You could correlate the carbon equivalent, your ATAS equipment to the charge mix, to the inoculation. And if you have enough plates of the microstructure of enough castings, like today, to give you an example, in medical what do you call sphere, MRIs of, let's say, to detect breast cancer, if there are lakhs of readings of these MRIs available today, the artificial intelligence can detect cancer even before the microscopic machines, the medical equipment can detect that cancer developing. It has come to such an accurate level of prediction that there is a very likelihood of this woman getting breast cancer in the following breast because of the various images that are presented. The same thing applies to your images for your microstructures, for the data accompanying it before and after, because this is what will enable us to go for actually the lowest cost, most precise, and accurate casting outcome that we should be targeting, all of us. I just wanted to share this vision with you. And I would also like to thank you on my personal behalf and on behalf of Rahul and my entire team and the people who are behind Rahul in the office over there, who are doing a great job in helping develop these cutting edge technologies. And I look forward to increased interactions with you. Having said that, we have many questions. Senthil, would you like to go through the questions for us, or shall I pose that to Rahul?
Yeah, it is better to you can go through that. Raj, please coordinate.
Mr. Rahul, actually, I think actually you can run through it.
Oh, me? You want me to run through it? Okay.
No, Mr. Rahul, sir. I told actually Mr. Rahul can run through it. So
Yeah, sure. Yeah, sure.
Can you read the questions, Rahul?
Yes, sir.
Okay.
So
Go ahead.
if you use more of borings, how it will affect the chemistry and soundness of the casting? So if you use more of borings, first, um, first we'll be needing more energy to melt the charge mix. That's very sure. Castings, yeah, tensile strength, it will be very difficult to get the tensile strength. But final casting, I think we'll have this question a bit often, because I would like to explain it in a much deeper sense. I think if we don't have much time over here. Also,
So
it's no big.
I can help you in a little bit over here, because there are two aspects to this question. One is the domain aspect, which Mr. Patankar can certainly put my colleague Mr. Patankar can talk about it, about the chemistry and the soundness of the casting. And the other is from Rahul's point of view, that is from the predictive prescription of the chemistry that we want to put up in the scrap. So, do you want us to address the domain side or the intelligence side? Which aspect do you want to know?
Mr. Godappa, actually, this is a question from your side, actually. So if you can let us know in what side actually you would like to get the answer. So,
Not a
sir,
problem.
yeah,
Yeah.
maybe you can talk on the domain side, sir. Actually, I think we are talking about domain. So,
Yeah. So, Mr. Patankar, would you just address it briefly, succinctly on the impact of borings on the, yeah.
Thank you, sir. Actually, the question of the use of borings in the melt has a twofold side effect. One is the higher power requirement or energy requirement, as mentioned by Rahul. And second is that because the particles what we add, every particle is acting independently and the burning losses are higher. So you have a very serious problem of the carbon drop in the melt, and you have to calculate your charge calculation. Raphatizers will be an additional material that we has to be calculated. So calculate first, make the calculations of the requirement and establish losses from the process of melting of turning borings and fines. And then once that is done, probably every other process is same as the what is explained by Rahul and the referred in the chart in front of us right now.
Thank you.
Hello,
And
sir.
yeah.
Sir, good afternoon. Sir,
Good
my
afternoon, sir.
question is, if you use more of borings, what will be the effect? What is the percentage of boring you can use?
JV, please
Percentage
take the
of boring, See, it depends on the source, because a lot of foundries have machine shops attached to their own company, and the generation of borings in their own shop is pretty high. And then if you are compelled to use higher borings, then your initial stage itself, because requirement of pig iron, requirement of solid scrap, these are all required because the particles of boring are so small that they tend to burn away because of the exposure to the high temperature. So
What
the
is the
effect of
percentage?
the
How much percentage you can restrict?
percentage depends on the, uh, if you ask me personally, a 20% boring addition is probably a reasonably controllable situation. But if you have to add more and more for any reason or commercial reason or a management decision, then you have to calculate and add those elements which are going to burn away in the furnace itself. So in the initial stage, your cost of uh, basic scrap and the cost of the borings will be the factor that you have to take into consideration. You can make any amount of scrap because of the constraint, but for a good casting, good output, consistent output, I would recommend a 20% cap on the charge calculation.
Okay, thank you, sir. Sir, one more second question. What may be the cause for the open grains and the shrinkage below the risers only in caster?
Can you please repeat your question?
So what may be the cause for open grains as well as shrinkage below the riser,
Yeah.
especially in caster?
Open grains, actually, the two situations are contrary to each other. Open grains are caused by higher carbon and higher carbon equivalent, and the shrinkage below the riser is caused because of the lower carbon, that is CE, and lower carbon.
Even if a higher C also cause the open grains, and even if the lower C also end up with a shrinkage below the riser, correct?
No, sorry, open grains are caused because of the higher carbon equivalent.
Okay.
And after machining the cylinder bore or whatever, you see as if it is very rough.
Mm.
And in the case of a shrinkage under the riser, because the feeding of the casting depends on the modulus and the requirement of metal from the furnace itself, the high carbon, if it is carbon is lower, you will have definitely problem of shrinkage in the solidification process.
Okay, thank you, sir. One more last question from my end.
Yes.
We have one compressor part, that's gearbox. Customer is expecting the hardness, uniform hardness throughout. Wherever you check, he wants the same hardness. How to achieve uniform hardness?
Uniform hardness is the issue of in a casting. If the casting is thin walled as well as with thick bosses, expecting uniform hardness in a thin section as well as a boss section is not practical. The reason why any specification gives a range, that if a FG200 grade requires a hardness of say 182 to 206 or 210, definitely
Wall thickness,
this
wall
range.
thickness is 12 mm to 50 mm.
Yeah. So what the variation of the casting plays an important role, and that's why when specifying the or creating this grades, there is a range given for hardness.
Yeah.
That you can't expect the hardness on a 20 mm thickness casting vis-a-vis 50 mm castings same. There'll be some drop of some points on the 50 mm casting section.
And
So
here
the
I would like
customer,
to, sorry.
the customer specifies the spot on which the hardness is taken, and that is a requirement. So once he specifies that, we have to choose the composition to make sure that that particular section gives the required hardness. But if you say I want the same hardness on a thinner section, then it is not possible.
JB, I would like to supplement your answer here from the
Yes, sir.
Digital or the artificial intelligence point of view.
Yes, sir.
That these are questions that foundrymen across spectrums ask every day. You know, these are not new questions. These are not new problems. These are common problems, except they are asked in different forums at different times, and different people have different experiences. I just wanted to draw my thought process with you, Mr. Gadappa, that if you, for example, have a digital interface like what Rahul showed you, for example, which also has a lot of other data capturing capabilities. And now you have, for example, in your mind, all the data on the scrap that you used, all the temperatures that you have used for a particular type of castings, you have all the relevant data. You will be able to do a clear cut root cause analysis of what scrap combination caused you the maximum problem, what gave you the best uniform hardness, and what inoculation gave you the best polytic or graphitic structure or whatever it is. These are answers which are lying hidden in the reams of data that is already being generated by you, but is not being actioned or captured for action by Foundrymen. I hope I make this point very clearly. This is a classic case of having a repeatable situation which can be answered very well within your own data sources. Just a point, Mr. Gudappa. Thank you. Thank you
Sir.
for your very good questions.
you.
Yeah, thank you. Yeah.
So thank you very much, sir. Thanks for your patience.
Always, sir. So also, if no pig iron affect on casting soundness, if we maintain required chemistry.
Sorry, can you repeat?
Also, if no pig iron affect on, I think his question is like, even though if we maintain the required chemistry and no pig iron, how sound the castings will be, sir?
Right.
May I intervene?
Yes, sir.
The soundness of casting is definitely when there is no shrinkage, the casting is sound. If you are talking in terms of the strength part of it, if there is the reason why we add pig iron, because pig iron is a blast furnace output which has a higher percentage of oxygen and it provides nucleation. Pig iron provides nucleation, natural nucleation in the melt, and it helps in forming the A-type flake graphite more easily than the non-pig iron cast irons. So you would tend to have a higher hardness on the castings where the pig iron is 0, and slightly better hardness and machinability on the metals where you have some pig iron added. So it's a question of nucleation and the microstructure, which is determined by the percentage of pig iron and the natural nucleation available with the pig iron material. Is it okay, Mr. Vodappa?
No, sir. This is from Chetan, sir. This is Chetan, sir.
Okay,
So
Chetan,
there's one
yeah.
more question which says actually furnace capacity is varied after running a new lining almost 100 kg due to slag deposits. At that time, how charge mix has been suggested? From Mr.
So,
Srinivasan Marimuthu.
yeah, Mr. Srinivasan, so basically the furnace capacity starting from the lining till the lining is broken out due to the wear and tear at the bottom side of the furnace, and also slag buildup. So the assessment of the metal availability, see there is a compensation of slag buildup reduces the capacity, wear and tear on the bottom side increases the capacity. So typically, if you are having a 1-ton furnace or a 1.5-ton furnace, you would end up in about 1.25 tons of furnace in the end. So your charge calculation, if you add the same charge, fixed charge, you will only find that it is maybe a couple of inches or millimeters below the top level. So whatever the space available and metal can be charged, the same composition what you have kept in the entire charge can be added without hesitation to maintain the chemistry. Am I clear, sir?
Sir, yes, but I'm asking about how they are suggested by software.
Yes, sir. So we give two options. We have as shown in the demo, sir. We have two fields. One showing the furnace capacity, other showing the operational capacity, the capacity that's under operation. So when you know that uh, your furnace walls are lined with slag or something, you can use those values. And based on that, charge fix will provide value. Let's take this current charge is suggested for 6,000 kg. If I just change it to 5,900 kg lesser, your suggestion will be based on that. Sir. So we have kept this column operation capacity where you can play with, sir.
Okay, but actually, what my question is, if slag deposit is not on directly reduces it to 100 kgs, it will slowly deposited in the furnace lining.
Okay.
So
Okay,
we
but
are talking of,
little bit,
we
it will
are
be reduced.
Yes, sir. As I
How?
told earlier, we need the help of digitalization over here, sir. We need to have a track of what's happened in the furnace also, sir, to get the
Even
correct.
slag deposition also monitored in this.
Yeah, somewhat similar to that. How? Yeah, we have to have the furnace event logs as well as the weighing scales of the furnace, so that what's the weight that's in the furnace can be tracked on a real time.
Okay, okay. And I have one more question in this. Actually, we have 3 days of material inventory in my company. Actually, every batch we have a lot of incoming raw material quality variations here. At the time, how we can able to suggest the charge mixes?
Yes, sir. So again, over here we have given the date and the lot of your procurement, sir. So let's say every day you're getting a new lot, sir, or new batch of raw material that's coming in.
Yes.
Each lot code can be segregated separately and for each lots separate on changing
You
the lot.
mean we need to follow about that first in first out things
Not
in
exactly
this,
first
right?
in first out, sir. Not exactly first in first out. Let's take MS scrap. You have four different plots, and each plot has a different chemistry. So all you have to each of these plots, and based on that, you can change it. Actually, I don't have any clarity. If I had some, so you can change the lots over here and its quality.
Okay,
Based on that, these values also can change the.
okay, okay. Thank you so much.
So just a minute.
I have one question. Can I ask? Bhushan here.
Yeah, please, sir.
So, just similar to the question earlier, let's say I have purchased 15 ton of material, some scrap material, right? Now,
Okay, sir.
technically, on the top floor, you dump all the 15 ton material, and the team will start. Let's say my bay was empty, so I use 5 to 8 tons of this material. Still, 7 ton remaining is there. Okay. Now I purchase
Sir.
another 15 ton of material, which is going to pile up on the below 7 ton stock of my earlier stock, right?
Yes, sir.
But melter person will lift the new lot which I have put on the bay. He will not mix the earlier lot. As well as nobody knows what is now out of these two batch current stock available. So in optimization, how would I consider which lot is going to use? Because practically it's going to hit the top new coil up stock.
Very good question. But
Can I answer your question?
एक कास्टिंग टाइप का असं क्रॅक झाला 120 140 मध्ये ते 1% पण नसते ते तुम्ही एवढा मोठा हायलाइट करायचं काय गरज नसते म्हणून म्हणतो मग तर काय
Mr. Gore, can you please
Raj, you have to put on mute. I think there are some crosstalk is coming.
I'm
My
muting it. I'm
question was
muting
clear,
it.
or should I repeat?
I'm muting it.
Got your question, so just so I
So,
can
Yeah,
answer
Mr.
now,
Rahul,
right?
you can go ahead. You can go ahead, Mr. Rahul.
Yes, sir. Thanks, sir.
Rahul, I would like to take
Yes.
that question from Bhushan. See, number one, Bhushan, if your process is completely non-standard, even to the extent that you are not able to segregate your lots of scrap, then you already have a problem, right? Now, the only way you can overcome this problem is you are having a disciplined storage of scrap. Point number one. Point number two is when you are using a particular batch of scrap, whether it is old batch, new batch, medium batch, then you have no other option but to do a spectral analysis and find the elements of that particular scrap that you are using and put that into the lot number that Rahul was just explaining in the software. In which case you will get the correct optimizing. But the software cannot guess that if you have three lots mixed and you don't know which lot is what, and you don't know your magnet is picking up which lot, I don't think any software can guess that, except by having some lead chemical element indicator, which might be able to distinguish, which the software can then distinguish. That, for example, that I have a specific element of, say, carbon, or I have a specific element of tin of 0.16 in lot number 7, then it will say, okay, this is lot number 7, and will give you the output based on lot number 7. Or it will give you an output based on lot number 5. Some lead indicator or element has to be available. So if you can do a handheld XRF there and get the elements tested, definitely the software will be able to identify the probable batch that you are picking up.
Yes, yes. What you are saying is right. I mean, what I'm trying to highlight here is the practical way of how Foundry, what I have observed is that because the bay for my CRC scrap is same. So if I purchase 15 ton and if I use 5 or ton or something, another new lot is going to pile above that. They don't have a separate space for same CRC scrap. It's just one bay for CRC scrap or MS scrap or something like that, right? So in that case, what you are saying, suggesting a segregation of the lot wise, that I see practically somewhere in the Foundry space constraint might play a role there.
So let me also then explain to you that we have got, I think Rahul will explain that we have put an uncertainty factor over there. So Rahul, am I correct? Can you show them the uncertainty factor role in this? Yeah,
Yes,
please
sir.
go ahead.
Yes, sir. So, as sir said, once you're going to mix up 2 to 3 lots, where the classic example of the chemistry from 4.1% to 4.3% in pig iron, then your uncertainty degrees, which will directly impact your cost of the charge. Till you'll be getting your chemistry, final chemistry first time, right? The thing is that your cost of the charge will increase. So if you see, you get the trade-off there. Maybe you can save the, but you have to pay it in.
Rahul, can you show them a demonstration of what happens when you put an uncertainty factor from 0 and then put it to 1? What is the change in the prediction given with the software? Yeah, that will make it. Yeah.
Let me feed in some values so that it looks as realistic.
So here Rahul is changing the values just to highlight the uncertainty. What Bhushan, this is in answer to your question, right? That if you are uncertain about the chemical elements of the scrap, you can put that in over there based on your estimate.
Yes, yes, correct. I think that needs to out. So this could be a good way to find out those uncertainty, which is not sure about which lot. Then maybe this could be a way. Yeah. Thanks a lot.
Exactly. That's what we wanted to highlight to you. So you want to demonstrate that, Rahul? Yeah.
Yes, sir, sure, sir. So here we can see I've kept the uncertainty as 0. Basically, you know what's the lot you're using and its chemistry. That means your cost will be around is per metric tons, so per kg. But once the uncertainty starts, certain of what's the thing in a figure. Don't worry, these things will be perfectly calculated by software. So you don't have to enter it manually every time. I'm just changing it for demonstration purpose. Iron is uncertain now. What happens? Okay. Composition.
So I think the chromium we have changed a lot, that should not be, it's
Sorry,
taking
sorry,
it as,
sorry.
yeah, correct. Yeah, that's
Hello.
Quite a lot uncertainty.
So good evening, sir. Ayyappan from Shakti Auto.
Yeah, hi. Yeah.
So we are facing recently one issue. Hello.
Yes, sir. Just a minute.
Yeah.
Yeah.
Last in casting, last solidification area, some brown dot issues happen. So,
Yeah, just a minute, sir.
some particular
Just-
inaugural patch using.
Sir, just a second. Rahul,
Hello.
have you been able to demonstrate it, Rahul?
Yes, I'm trying it, sir. The thing is that I'm not able to exactly quantify it, so that's the thing. My value is not changing. That's right.
It doesn't matter. I think he has understood. Gushan has understood that. Don't worry about it.
Oh, okay, sir.
Yeah, now Shakti Auto, you were saying something. Please go ahead. Yeah.
Hello.
Yes.
Sir, actually we are getting, we are producing safety critical components like steering knuckle and passenger cars. We are getting brown dot issues in the last solidification area. If any reasons for the raw materials or inoculant thing, what the reason for that, sir?
Sir, that is a domain question because now we have to understand the inoculation specifications and what has happened in that batch, whoever is the supplier. So that we will take it offline. If you could please contact us separately, we will be able to take that offline. Okay. Yeah.
This problem not coming for raw material.
Not necessarily. I mean, I can't answer that question in 100% accurate terms right now, but we can analyze that for you and let you know. I can't say yes or no at this point. Because there are many reasons why that brown patch comes. We have seen it many times in many instances in many foundries. It comes, it goes, but we have to determine the root cause.
Yes, sir. So
Not understanding, sir.
We will get back to you, sir.
Okay.
Okay, Mr. Senthil Kumar, any further questions or shall we call it today?
So I think we can close the session actually. So moving forward, actually, I'll formally close the session actually by vote of thanks. So good evening again to everyone. As we come close to this insightful technical webinar on behalf of Institute of Indian Foundrymen Chennai chapter and MPM Infotech, I extend my sincere thanks to all those who made this session actually today a great success. First and foremost, I had gratitude actually to Mr. Deepak Chowdhary, founder and owner of MPM Infosoft Private Limited, for sharing his rich industry experience and practical perspectives on cost-effective charge mix and optimization. We also thank Mr. Rahul for his clear and analytical presentation, highlighting the role of technology and software in achieving robust Foundry solutions. With moving forward, actually, I think we'll be having some more sessions like this actually, and we look for everyone to participate. I can see almost like 90 plus peoples across India. So it was a great thing actually to meet everyone under one platform to discuss further. Thank you once again to PM and Mr. Deepak.
Thank you, everybody. Thank you very much, gentlemen. We are very grateful for your patience.
Thank you.
Thank you, sir. Thank you.
Thank you, sir.
Thank you so much, sir.
Gratitude, sir. Thank you. Bye.